Jefes here, the condensed matter physics section of the Royal Spanish Physics Society, and it's my great pleasure to introduce Professor Clivia Sotomayor. She was born in Chile, she studied physics there, then after Pinochet's coup d'etat she moved to Manchester for a PhD degree, and then she got a postdoctoral position in Scotland, then she moved for a permanent position in Germany, then to Ireland, then to Spain, in Instituto Catalán de Nanotecnología. I met her there in the framework of the Nanolito network, and recently she was appointed as the director of the INL, the Iberian Institute of Nanotechnology. She has been involved in research in semiconductor, in nanoimprint lithography, and more recently on phonons, physics of phonons. She co-founded one company, Photonics, and she has now an ERC grant on the propagation of information using phonons. She has been very successful. She got many awards. She supervised more than 20 PhD students and 60 postdocs. And it's my great pleasure to introduce her. If you want to know more information about her life, her passion, you will become impressed through an interview I made to her in my podcast, Conferencia, and I recommend you to listen to that podcast. Thank you very much, Clivia, for your talk.
Good morning. Thank you very much, Rosemary, for the kind introduction, and my thanks to the organizers, Jerome, and of course to you all for being here. The topic is not typical. Phonons are not well known, certainly not very popular. Everybody tries to avoid it. Basically, the work has been done at ICN2 in Catalonia, but it started many years ago when I was already in Germany. At present, I am in at Bienal. Bienal is in the northern part of Portugal, and is an institute created by the governments of Spain and Portugal. It's an intergovernmental international laboratory. It has some 500 people and also has very large facilities. It's a beautiful place to work. We have primarily topics in personalized health and food, in energy and the environment, and information communication technologies, with examples of the latter on photonics, spintronics, etc., 2D materials, quantum computation, and NEOs and MEMS, and a very strong couple of engineering groups. We have taken the opportunity of a change of position to strengthen the links to Spain and to Spanish colleagues, and one of the first initiatives was a collaboration workshop with colleagues of Zaragoza that took place in May, and more recently we had also a very intense 2 days with the colleagues from the newly created Iberian Center for Energy Storage. So there's a large initiative going on there because it's like a sister center to INL. So I will try to go a little bit through the motivation background and then go to see whether we can guide phonons. Phonons, typical, classical, and our attempts to produce topological waveguides and observe phonons in those. Before I continue, I have to say that the body of knowledge, effort, techniques, etc., that has been used in this research over almost 2 decades is a result of collaboration with all these colleagues here, and these laboratories, and also with some European and national funding. So the first thing that came up was in Glasgow University at the Nanoelectronics Research Center, where in addition to studying excitons in nanostructures, we were asked to see if our techniques could say something about reactive ion etching damage to the sample. So one of the experiments was to look at Raman scattering. Is this a pointer? Okay, so top left. these pillars are gallium arsenide nanopillars, no quantum wells, no nothing, just deep edge gallium arsenide, 80 nanometer diameter, 500 nanometer tall. So by that time, 1990, they were really state of the art. And we changed the surrounding to see the effect of a dielectric constant, and we had, okay, okay, so we first of all observed that I'm not getting very much time. Okay, first we run a scattering there in the angle, and by doing this, we couple to the wave vector not only on the allowed surface, but also on the side walls, breakage of selection rules, which allows us to see other features, first of all for living phonons, but also to see the shift of this other of this shoulder, which gave an indication of the impact of the shape of the material. And then by changing the refractive index of the material surrounding it, we could follow the Ruppin-Engelmann approach, equations very similar to those used in plasma physics. The model did not include polaritons, but neglected retardation effects. So that means that we lost a little bit of physics there, but these were the first phonons that came into my life, after the one from my PhD, of course. We looked also at thin membranes. These were normal membranes of silicon. You can see that they are a cross-section, wrinkled because there were no stressors at the time. And we look also at the acoustic phonons as a function of confinement, that is to say for different thicknesses from 32 to 38 nanometers. And we studied this and we proved that there was confinement of acoustic phonons, the frequency depending on the thickness of the sample. Many years happened in between until I basically went back to phonons because of the concerns of electronics concerning power consumption and electricity use, and basically looking at information communication technologies, quality of signals, huge consumption of artificial intelligence, of that, etc. And then we noticed a real societal challenge. The use of artificial intelligence industry could consume as much energy as the Netherlands by 2027. So this is a little bit of the other side of the Green Deal, the digitalization, etc. And one of the main users of energy, in addition to the 0 to 1 and 1 to 0, is indeed the interconnects. I will not give you a lecture on interconnects, but suffice to say that which physical entities carry information and perform communication? Well, we all know fermions, photons, phonons. The important bit about the latter is that the phonons in question have very small energy. So it's orders of magnitudes. And so there is a case for exploring phonons, perhaps first to transmit technology and information as interconnect, and maybe later, if we succeed with the interconnect, a computation. In the quest to understand phonons, to measure them, compare them to models, we developed a number of techniques, some of which are listed here. This is a review article by Ryan Gay, and these are all tested in our laboratories. And I encourage you, if you have interest in phonons, to take a look, because we really did a comprehensive job in this review article. One of them refers to the use of laser Raman scattering. So here we track the frequency of optical phonons in a material, here this happens to be a 2D phonon crystal, where we hit from the bottom and we scan with a laser on the top to measure the frequency of the optical phonon. And that, based on power, thermal conductivity, size of the spot, etc., and the decay of the phonon, of the heat profile, give us an indication of the thermal conductivity. So this method is very nice because it's contactless, but it requires that you have access to a bottom river sample. we measure the phonon dispersion relations by blue and light scattering. So here we have membranes of different thicknesses from 27 down to 5 nanometers, and they're compared to finite element analysis, fit, and you can see the calculation here, and we focus at the gamma point at the very low energy. And we see that all the features that appear in light scattering give us indication of the various wave numbers. So this allows us to say if we design a structure with a particular phonon bind dispersion, we're able to measure it and compare. One key question with working with nanostructures, as you might probably guess, is surfaces. So here we have a model of a membrane, pristine membrane, freshly etched, after a time when there has surface organization and reconstruction has been allowed, and then it's at ambient temperature and conditions, the oxygen starts to be incorporated, and eventually you have, I wouldn't say so nicely square like here, but you have a profile that has dangling bonds, oxygen and silicon in this layer. This is what's known native oxide in silicon, the thickness of which between 1 and 2 nanometers. And we study samples, the real samples, and we basically can learn to measurements of the thermal conductivity for the various conditions. And the measurements were analyzed in terms of this accumulation function to say what proportion of the thermal conductivity is carried by phonons of a particular mean path. And this was to us very telling, because it basically says that when you have phonons, entering calculation of phonons into anything, you need to make sure that you have a picture of their distribution. How many, and at what frequency, and in some cases of what polarization. So when you look at models, and when you look at commercial models to give you the heat dissipation in materials or devices, it is crucial to know what assumptions have been made. Because in this regime of 1 micron downwards, you see that, for example, for 50% of the heat is carried by phonons of 20 nanometers. But there are other numbers as well, so the story is not complete. Furthermore, we know that phonons are bosons, and that they have a distribution, a density of state, that is changing in time as they decay. So one of the key issues has been pointed out and has emerged relatively recent is the term or the concept of participation ratio. So that tells you the fraction of the atoms that are participating in a given mode. So it goes really down to the atomic scale. It gives you an idea of what happens at interfaces. But the picture here looked at nanometric surface resonators, where for us the point of interest are close to the zero because we work in the here. It's not easy to calculate. Our colleagues will tell you that from Siesta and other methods. So in this respect, here is my take on the perspectives that we have in terms of heat transport in the nanoscale or nanostructured matter. First of all, we need to control or account for the surface resonances, and not just the surface resonance in a pretty symmetrical shape, but defects, dislocations, atoms, etc. We need to apply the concept of phonon participation, both structurally and dynamically, the time scale. We need to account for disorder, and for that there are some beautiful calculations in this paper by Erickson, as well as in surfaces accounting for the stress and the strain. Every time we make a nanostructure, we have these concepts of strain and strain coming up in our calculations. So there are simulation work by our colleagues, which is very intricate. It's full of physics, but also full of many questions. And urgently we need technologies for both, for controllable and scalable material characterization, if we're going to harvest the benefits of phonon quantization. For example, towards thermoelectric generators in the nanoscale, and in terms of heat management in electronic materials. And then, of course, there's always a need for experimental methods, because in this field, if you do not have the same result or the same information by an alternative technique, independent of the first one, you cannot possibly trust your results. So let me just jump this one. This is very pretty, but I don't get there too fast. There's a lot of fun in physics when you couple phonons and photons, and we do this in optomechanics. So an optomechanical nanobeam is shown here. Optomechanics is radiation pressure, is the force that enables the detection of gravitational waves, is what you have the interaction of radiation pressure that gives shapes to the tail of comets, etc. So in the physics of this optomechanics, you find beautiful examples of a coupling of phonons and photons. We have also taken a peek at magnons, which is promising a lot, and also electrons and phonons. Challenges appear to understand, for example, the quasi-bosonic nature of phonons. I say quasi because phonons are basically defined as a collective of lattice vibrations, whereas photons are a single quantum of electromagnetic radiation. So you have like the many body part and the single body part of bosonics. And harmonic decay or harmonic scattering is what plagues many of the experiments, and we would like them to be clean, because phonons decay, change their frequency of their energy, and redistribute the density of a state. So your initially beautifully designed density of a state goes to pot as a function of time. And this calculation is non-trivial at all. Maybe the simulations of quantum computing will help us there. Behind the phonon physics is a question of engineering, and here there's a huge amount of issues concerning the role of noise and fluctuations, and for us, the exciting physics comes in the protection of the phonon transport. And pretty pictures here relate to multimode optomechanics. It's a very beautiful work one of our postdocs carried out. We get the funding to do this work because we promised, and we had to promise circuits based on phonons at some point. And we actually had a beautiful concept. Generate phonons from surface acoustic waves, detect them likewise, bring these phonons into an optomechanical nanobeam, which has an area where both photonic and phononic confinement takes place, read them or address them with an optical waveguide, and you have a whole lot of sequence of processes involving phonons. This concept was realized. This is here on silicon with piezoelectric aluminum nitride, surface acoustic waves, etc. And to cut the story short, we were able to observe our signal at about 2 gigahertz, and looking at the efficiency of the optomechanical coupling, that is to say the number of coherent phonons in the optomechanical beam, we were able to, first of all, generate something like 220 plus phonons per microwatt, which means that you have phonons well below microwatts, and some of them may be pushing to the picowatt of energy. And then we calculated that we had 2.6 phonons in the cavity at room temperature in silicon. So this is setting up now the scene for a number of other projects that we are involved in. There's plenty of nonlinear physics as well. It's a beautiful system to study chaos synchronization and back, to study the injection locking. All the features of nonlinear physics happen in optomechanics involving phonons. And let me now go to the mechanical waveguides. So this is a phononic crystal. You may not recognize it as such, okay? It has a band gap. There are examples of that, simulation of that. And in the second one, measured by Reunión scattering, where we had stokes and anti-stokes in the scattering spectrum, the Rayleigh scattering line. And this is the area that gives us the band gaps in our structure. We compare the frequencies of these features as a function of angle to obtain the dispersion relations. And we had, okay, we forget about the numbers. And we had a design putting two of these phononic crystals facing each other, creating a phononic waveguide in the center. So we recover our phononic band gaps, and by placing the laser in the region of the waveguide, we were able to pick up phononic waveguide modes. So this is very pretty, very exciting. We compare these to the simulation, but they didn't fit quite well. Okay, some animations. Why didn't they fit well? They didn't fit well because we had a sidewall angle. It was not a straight sidewall. There was a tilt. And if you, okay, so you see what happened when you increase the tilt, you basically close a gap and you change the dispersion relations. So control of nanofabrication down to these few nanometers and tilt angles of a few degrees seems to be very, very important. But more important, it comes in the case when we want to study topological phononic crystals. So the calculations here were made for both isotropic and crystalline. Isotropic means nanocrystalline silicon, and normal crystalline silicon. So we calculate bands, the projection in X and Y, and then we basically define a system where we find a single Dirac point as interfered. At the point K here, however, we open a gap inside the Dirac point. We'll see that. And the unit cell in this case, to open the Dirac point, had features of this shape, small and larger triangles connected by bridges. We had in the regime of gigahertz a gap of about 1 gigahertz wide, which is very good. Here you have a slight variation of the unit cell dispersion, and that gives some indication of the movement in the features, in our triangles. An estimate of Richard numbers, very optimistic. And then we define a topological interface by placing two of these unit cells back to back to give us large triangles inverted, and this would be defined as a topological interface. And what's important to see, you have it here. What happens when you start to change, important, these are phonons, these are masses. When you start to change the distribution of the mass density while keeping the symmetry. So here you see how the gaps are closing and the mode is approaching from the bottom part to the higher part, and then when things are pretty much the same, this process reverses, and you have a gap band, gap mode coming out from the upper part. So that simulation only. The displacement, you see here the interface. This is again back to the interface. You see that basing involves two parts, the two unit cells that are back to back at the interface. So it's a fairly localized system, and we call it waveguide. I think we did a number of simulations, and we home on a few to fabricate. So these are silicon membranes with patterned phononic crystals. They were realized at VTT, at the Technical Research Center of Finland. We asked our collaborators to calculate properly the shell numbers, which they did, and they're not exactly half, but somehow very close, and they are affected, the very curvature and the shell number are affected by the precise symmetry of the unit cell. So there is a trade-off here of amplitude and frequencies versus the topological invariant. We just ran some experiments looking at this type of zigzag interface, and we managed to obtain a brilliant light scattering spectrum or spectra, and the feature of interest are around here, and then we moved to ANL. But we started again, so I think we will have news for you in a few months, whether it is the mode, whether it is protected, and compared to simulations. So what we have now in progress is something to address the next step. And the next step is, do we have the right waveguide modes and non-trivial topological phononic modes? I think we probably do. But do they propagate? And can we measure the propagation losses? Or no losses, which would be the ideal case. And this is really the proof of the pudding. We need to look at propagation. And we have tried very hard before we packed the lab in Barcelona. And it remains a challenge not only for us, but also for other colleagues who examine similar samples. So we decided to use vibrometry. Right? Vibrometry is a laser double vibrometer, measuring the variations of the thickness, but we need to measure along the waveguide. So here we are. This is preliminary experiments at 1 gigahertz, and we are now going to our 2.6 gigahertz measurements, and hopefully we will have something for you in the next years. So my take on this is that we were working by analogy. Now we know the topological invariance. We lower our ambition to work up to 2.6 gigahertz instead of 14, 15, because of experimental methods to detect this. Our designs have, of course, respected Dirac Phonons at K and K+. We have a gap at around that value, but the real issue is the aim of the ERC project I have is to demonstrate propagation and hopefully protected propagation of phonon modes. So fabrication challenges, many. Fabrication characterization challenges, many. If these features are hundreds of nanometers, even if the little ones are 40 nanometers or so, it means that a lot of your laser light goes through, so your scattering is seriously compromised, and you get bad reflections that you need to remove of a pattern that is not trivial, something like this. However, I think there are very exciting possibilities still, and if we crack it, if we can demonstrate propagation of phonon in a waveguide, I think the problem of low energy interconnects is solved. So, to conclude, propagation issue, a lot of physics here in device relevant physics at room temperature. We need to fulfill these expectations first before we go to computing with phonons, for which there are some models already proposed. And we need to have creative ways to control the phonon density, but not just the band structure and the phonon density, but also its, more importantly, dynamics. And with this, I hope I haven't bored you too much with my phonons, but thank you very much for your attention.
Thank you very much, Clivia, for this great talk. You have to take a flight, but we still have 2-3 minutes for taking a couple of questions. So.
Thank you very much for the nice talk. I have a question. So there is a a database that was created about topological phonons in natural materials without being engineering like you are doing, right? So you think this is possible to also reach in natural materials, or what you are really targeting is that something like in the surfaces of topologically non-trivially systems with non-trivial topology of phonons, or what you are really targeting is because these integers in this really frequency range, because it would be at higher energies, I guess, if you have something like that.
Okay. So the motivation is really to lower the power consumption of electronic circuits, so we can continue to play with ChatGPT and so on. But really is an engineering-driven research question. We know there are topological materials that are naturally occurring, but our intention is to work with something that can be integrated with silicon, and this is why we're going insisting on silicon-compatible materials. There is, of course, a promise of using two-dimensional materials, like polyethylene disulfide and others. There is a promise of using model structures. We have to pattern them, and here I have to be very friendly with Jose Maria because I want to use the helium microscope for patterning my structures. So there is plenty of scope, and I think it's not exclusive, this approach. We can use materials, but they have to be reproducible, integrable, and this, as a condition sine qua non.
Clivia, thank you for a very nice talk. I have a question. There have been some recent work on phonons that carry angular momentum in addition to linear momentum, and particularly in the context of electron transfer and electron-phonon interaction. These are so-called chiral phonons. So I want to hear what you think about these chiral phonons.
Well, in analogy to topological photonics, where the issue of topological protection of photons has been achieved by using chiral phonons, which are also a directive for quantum photonics. But it seems that chirality is one of the key issues here that could give us a handle in these protected topological states. So if we look at these structures that we have designed using the zigzag configuration, there are several ways in which we could achieve chirality. So like the log of Mayer-Sigrand is one approach, for example, only that it doesn't have all the details in it. But it's structurally deforming the sample, the position of structurally deforming the distribution of mass density in the unit cell. And I think if we move away from silicon, or if we have a layer of silicon nitride or piezoelectric below or above, we could achieve that. So to go to the electron-phonon interaction, that may be a bit more complex, a bit out of my depth there, because in the materials that we study normally, we have deformation potential and similar phenomena. The silicon that is preferred is isotropic, which doesn't help very much with this. We could go back to crystalline silicon and start looking at how do we engineer, based on the properties, chirality, aided by a suitable design of the structure. Key to all this chirality, in my opinion, is how you activate it. You have to launch it, you have to control it, you have to drive it. It's no good if it is passively chiral. It has to be addressable, in my opinion.
It's 1 minute to 11. Would you like to take the last question, or? Yes.
Hi, I was wondering if, so you have waveguides, you can localize the phonons. Have you considered about whether or not you can make them interfere, or whether you can build an analog of a beam splitter, say?
Phonon interference has been seen in phonon echo experiments some years ago in the group of Professor Fröhlich in Dortmund. There's some beautiful physics. I think at the moment, to make them interfere, we would have to have coherent phonons, first of all. That means that we would have to master the conditions for coherent modes that will not decay, neither surface or otherwise, and that will live sufficient long time to allow this interference to manifest itself. I think it's a doable experiment, it's a hero experiment, but based on the flexibility that phonon waveguides afford us, it could be a reality. Thank you.
Okay, I think it's high time to close the talk and thank Clivia again.
Will we continue with the dialogue? Please, Ricardo, Jonathan. Ignacio.
Okay, so now it's working. So good morning, everyone, and welcome to this very first dialogue among those that have been included in the program of this conference. My name is Ricardo Díez Muiño. I'm the director of the International Physics Center, which is a center that is a research center located here in San Sebastian. So the title of the dialogue is the quantum revolution in the 21st century, and the basic idea behind, or the basic concept that is behind this title is to say that, okay, I think we know, I don't have to convince you that I think for all of us, science and technology, they are essential to understand our society from many different points of view. So they shaped and they framed our life from the economic point of view, from the philosophical point of view, from the practical point of view, from many different points of view. And within this general concept, physics, and in particular quantum physics, it also plays, I would say, a crucial role in all this. So this has been the case in the 20th century, and we believe that this is going to be also the case in the 21st century. So Luis Viña, the president of the Royal Spanish Society of Physics, he reminded us that the next year is going to be the quantum year, so this is a year that really devoted to quantum. So there's a lot of talk, discussion, and hopes, as we have learned, put into quantum physics, quantum sciences, and quantum technologies. So within this general framework, or let's say in this general context, so we will be discussing precisely which has been the role of quantum physics in the past, which will be the role of quantum physics in the next decades. And for this purpose, so I think we are honored and privileged enough to have with us the two outstanding scientists that they work on the topic. So I will be very briefly introducing them. Ignacio Cirac, he was already, I would say, providing one of the best introductions for this dialogue. Jonathan Holm, he will be providing also a talk next Thursday, is it Wednesday? So let's say the profile of both of them, the profile of Ignacio was already introduced before, the one of Jonathan will be introduced on Wednesday. But let me just briefly mention that in the case of Ignacio, he's a director of the Max Planck Institute of Quantum Optics in Germany, in Garching, right? Well, he also coordinates the consortium of theoretical quantum computing in the Munich Quantum Valley, which is one of the hottest spots, I would say, about quantum physics in the world. As we learned before, so he actually studied in Madrid, in the Complutense University. He then moved to Castilla-La Mancha, then to Boulder, to Innsbruck, then to Munich. And he's a theorist, and we already learned what he's mostly devoting his time to, although I will ask both of them also to provide some words of that. In the case of Jonathan Holmes, he's professor at ETH Zurich. He actually made his first undergraduate and graduate studies in Oxford, right? He also was in Boulder, which is also another hot spot for quantum physics in the world. And well, actually, let's say, rather than explaining to you which is the expertise that they have in their research everyday life, I would like to start, let's say, asking them just to provide in very few minutes, which is, let's say, not only their current interest, but which has been their career and which has been the topics in which they have worked and they feel more proud or excited about them, and that it can also provide, I think, some kind of general context for what you are doing in quantum science and technology. So, Matthew,
yes, so I guess I'm an experimentalist. I study the control of individual atoms, charged atoms. They're extremely clean systems that can be well isolated. They were sort of original atomic clock systems. When I got into the field, they had been demonstrated as basic components for doing producing entanglement between pairs of objects, and the perspective was clear that a big challenge for the next generations would be to try and build quantum computers. And I think ever since then, that's inspired my thinking, is how to, in fact, scale up from these very small systems to very large systems. We think we need thousands of particles put together for quantum computers. And that's a nice challenge in the sense that it's a mix of physics. You have to understand the physics extremely well, and you have to delve into new technologies and bring those in, because scaling is kind of the interface between technology and physics. And I think the other thing that really is inspiring is that those new technologies always provide new capabilities for control, and that gives you access to new quantum states, new ways of controlling quantum states. So for me, I think one of the interfaces that's interesting is that between quantum systems that are very well isolated and open quantum systems interacting with their environment. Ignacio already talked about that today, and we've found methods, or some of the methods that actually Ignacio proposed, for driving systems into interesting quantum states based on using dissipation, engineered dissipation. And I think some of the things that I would be proud of in that context, we were able to in the last years based really on something that looks like laser cooling. So this was fantastically simple compared to any concept I had of doing error correction, but this was really something that came out of a side project in dissipation and quantum optics. So nice surprises in the physics.
Okay, so in the past, so I've been working on, the question that we addressed was how to build quantum devices that would do something that you cannot do in the classical world. So we started thinking about how to build quantum computers with ions, then how to build quantum simulators with cold atoms in optical lattices. I mentioned that in my talk. We also thought about how to build quantum repeaters using atoms and light. And so this was part of my life in the 90s. Then in the 90s I also started working on quantum information theory. That's an abstract theory. That it's the one that is supposed to be behind of quantum technologies in the same way that now when you use a classical computer, you don't realize that there's a mathematical theory behind that was developed by Shannon and many other people that allows you to compress information and do many things with information. So the same thing happens with quantum systems and with happening with quantum computers. There will be a theory behind it, and that's the theory that's called quantum information theory that I was working on in the past. Then in the year, around the year 2000, I moved on and started working on tensor networks. They're called tensor networks, and so the basic idea there is that inspired by the tools that were developed in the field of quantum information theory, then we found some ways, me and other people found some ways of describing many-body quantum systems, let's say classically, so without the help of a quantum computer. And this gave rise to what is called tensor networks. We started building, on the one hand, algorithms for classical computers to describe many-body systems with tensor networks, and on the other hand, using tensor networks and showing that indeed these describe very well quantum many-body systems in thermal equilibrium. And then we, other people study how with this tensor network you can classify phases in condensed matter physics, you can do many other things with that. And so this has been in the past. I'm continuing working on tensor networks, and so lately I'm also working on quantum algorithms. So how to use a quantum computer, a quantum simulator to solve something that is difficult to solve with classical systems, and also in particular studying the role of errors in quantum devices. So if you have some errors, so can you correct them, or if you cannot correct it, can you live with them and still get some advantage? And so it's a little bit explains what is my background and my current interest.
So I forgot to say, please feel free to interrupt with yourselves at any moment, because I think it will make the dialogue more fluid. I will be posing questions, but please avoid that. So actually, let's say, we prepare kind of a script, but I think I will brief jump already. So at the very beginning, because listening to you, I also was curious to know how do you see the role of, in general, let's say, theory and experiment, right? Because you are theorists, you are experimentalists. So in this particular field, how the theory is leading experiment, how experiment is leading theory, because quantum, in general, quantum information theory, quantum computing, it was for a long time a very theoretical activity. Now, let's say, with all the capabilities that you can have with, let's say, trap ions, neutral atoms, or whatever, actually you are also leading some of the way to, right? So I don't know how you see that. I wouldn't like to say who is leading theory or experiment, but how do you see this role of, in this particular field?
If I may say, so experiment has been always inspired theory. So at any time you see what experimentalists can do today, and you can think of what they can do tomorrow or the day after tomorrow, and then this inspires you. And actually, most of the work on quantum information and quantum optics theoretical work has been inspired by experiments. Then it's a circle that closes, because then the proposals that you make and experimentalists are able to do it even much better than what you thought at the beginning, and then it fits back and you think that it closes the cycle.
I think there's aspects where the theory jumps ahead. I think most of us in experiment, we've been heading for 30 years at the same general theory that people produced a long time ago, right? One nice aspect there is quantum error correction, which was discovered in the 1990s, and people said this will be necessary to build computers that can beat down their errors. And for there were lots of theory happened extremely rapidly at the end of the 90s, so you could say everything was done at some level. But then and there's been continued evolution of that theory, but only in the last 5 years or so could experiments really access these areas that were proposed. And I think what's been nice there is that as soon as you have the experiments, there are actually very tailored errors that pop up in those experiments that the theorists could not have predicted that this would be the type of errors. And so immediately people have been able to see shortcuts for how to implement quantum error correction. They've realized that they can take advantages of some of the biases of some errors occur more than others to produce better codes. And in a sense, the theory was waiting for the input from the experiments in order to sort of give it more constraints, because the constraints of experiments are real, but also it gives some advantages because maybe the errors that are occurring in the experiments are simpler than maybe you can anticipate theoretically. So I think there's a very nice integration during the experiment.
Okay, so thank you. So as I mentioned at the beginning, so the goal is also to make a projection into the future, whether we all know how difficult this is. But let me first, before doing that, I think it's worth also to look a little bit into the past, because we are talking about the title of the dialogue actually was the quantum revolution in the 21st century, but one may say that the quantum revolution was already, or there was another quantum revolution already happening in the 20th century, right? I mean, we are physicists, we know what quantum physics has been doing in the last decades, in the last century, I would say. So I would like also to ask you, let's say, which even in this general framework, which do you think has been the role of quantum physics in the 20th century? So, because you can look at that from many different points of view, right? And you can look at that from the conceptual point of view, from the physics point of view. You can also look at that even from the philosophical point of view. We all know the connections between philosophy in the 20s, in the 30s, quantum physics, relativism, things like that. You can also talk about economy. So sometimes you have the estimate that almost 1/3 of the world economy could be based somehow, on quantum physics. So there are many different perspectives. So which are the ones that you consider that they are the most important, the ones that are more relevant for you? How do you see this general economy?
Quantum physics is somehow everywhere. You're right. The transformation from 1920 or so to 1960s, when silicon suddenly blew up and produced everything, is remarkable. And it's remarkable not just it's the technology that we live our lives by, but philosophy changed, because suddenly, I was just reading Heisenberg recently, right? You can't have this absolutist view of matter, but you rather see that fundamentally there's something outside our usual perception that we have to make an abstract description of. And this is a big change in the way we think. But I mean, in terms of impact on our lives, we're all carrying laptops that are full of basic solutions to Schrödinger equation being used en masse, right? And so it's been an amazing change, I guess, in lives. But how to separate that from the general evolution of technology, which keeps changing our lives? I think that's quantum clearly is the ground physics theory, if you like. It underlines technology.
Well, in my case, I share what you're saying, and I mean, it's clear that it has changed our technology, but leaving that aside, I think that physics has produced two things that are very important. One is the conception about nature. I mean, we don't, before quantum physics, so nature was something that was independent of the observer. And it took quantum physics to see that, I mean, nature is defining itself while you are observing it. And that's a concept that I think that it's very revolutionary. I think together with Gödel, the results of last century, that in undecidability and so on, I think that these are really main things that change a little bit the way that we look at everything. So before, in the 19th century, we thought that everything can be predicted, everything can be calculated, everything is determined, we know the laws, and as long as we have them, then everything is solved. Now with these two results, quantum physics and Gödel, and this tells you that actually there are things that you will never be able to solve, to decide, and not even to measure, and then there's randomness, so this changes completely. That's one part. The second important part of physics is the precision that we get with this theory. I mean, we can make a prediction about a measurement in the lab, which will be 1.002348 with 15 digits. And then the experimentalists go to the lab, measure, and then they measure these 15 digits. And the 16th does not agree because experimentally they cannot reach it, but you can get an absolute prediction that no other theory has had in the past. So it's not only a very revolutionary theory in the way that we think, it's not only in the way that it developed the technology, but also it's the most precise theory that we can ever imagine.
Actually, concerning precision, and just going back to the question of theory and experiment, right? I mean, you may also think that at some point you may lose this precision and then something new might happen. Let's say you may need some additional concepts, theoretical concepts, because at the end, experiments, they are also leading the way like this, right?
Yes, I think the experiments today get to such high precision that they start to constrain the standard model as much as you see in colliders at very high energy, right? So that you start to see that for instance, we are recently measuring nuclear effects, and we start to see that we need higher order reactions to nuclear effects in order to describe what we're seeing in the lab. When we're really observing from the position of an electron that's a million times away from the diameter of the nucleus, but somehow the tools that have been developed in this domain suddenly give us really strong insight, and they counteract the theory again in a different way, right? This is the constraints of quantum physics are fantastically strong at some level, and the experiments play along with that.
Yeah, so it's amazing because you talk about technology, you talk about let's say philosophy, I would say, and you also talk about precision. So these are like the three main ingredients. Okay, so with this in our let's say in our past, so I would like also to ask you which is the current status of let's say quantum sciences, if you want to call them in this general, perhaps not well-defined thing. So because if now new things are arising, or let's say a new hype is arising about this, so I would like to ask you why do you think this is that, and in particular which are the most important, I would say, physics discoveries or advance, if you would like to call it this way, that you think that is leading this way, you know? So because I mean, if we have all this behind us, so what is new now? So what's going on for having again this, let's say, excitement of quantum physics?
Well, I think that that's a big hype in quantum computing especially, but that's very natural. This has always happened. I mean, there is all of a sudden somebody comes and says, I can do something that nobody else can do, and it will try to do with a classical computer. It will take 2 billion years. That creates excitement, and everybody starts thinking what to do with that. And I mean, there are media, there are investors that want to make money out of that, and then this becomes a hype. I mean, that's unavoidable, and it's like that. But this doesn't mean that there is nothing that's important behind that. I mean, that there is a task that we have to develop. We're building this quantum computer, building these quantum devices. I mean, participating or creating this quantum revolution, and that's something that is happening. So now going a little bit back to the question. So what are things that have led, let's say, to the moment that we have now? Well, I think that I mean, people, if you look back, then you will see the different milestones in quantum computation. So one of them is definitely the paper that I mentioned here. So Richard Feynman was a visionary, I mean, showing that quantum computers can do things that it cannot do classically. There had been a paper before by some Russian scientists, but it appeared like in a half page, and where he said something, but it was real. Richard Feynman, the ones who really developed the idea of quantum computation. I think that the other milestone was given by a computer scientist, Peter Shor, and that it turned out, since he studied at Caltech, that he took quantum physics as that you study computer science, and then in the US, then you can take some other subjects that you like. And so he took just quantum physics, learned quantum physics, and this allowed him to come up with the 1994 Shor's algorithm, which there had been some results in computer science showing that with quantum computers, under some conditions, they call it oracles or something like that, then it can have some advantage. But it was the first time that Peter Shor showed that in a real problem, a quantum computer can beat any classical algorithm. That was an important point, because this made people take serious this quantum computation. And then it was again Peter Shor, the same computer scientist, who 1 year after that, or 2 years later, developed quantum error correction. And I think that this quantum error correction has changed physics, in fact. So it's the fact that the computer scientists made the discovery that physicists were not able to discover after 100 years of quantum physics. And so that's the possibility of undoing decoherence. So we always thought that if you have a decoherence in the system, then this will drive you to some state, and you will lose the memory about the initial state, so you will not be able to recover the information whenever it's lost in the environment. And so what he showed is that actually you can use computer science and think that you can restore the errors, and that's something that is useful in quantum computation, and is also useful in physics. People talking now about black holes and quantum black holes, now I think that there's a quantum error correcting code inside, and so this has, I think, that influenced a lot physics. And I would say that these are three important. And of course, then there are all experimental developments, theoretical developments, and so on. But I would say that these are really extraordinary achievements.
Yeah, I mean, the excitement is somehow, if you look back to the 20th century, we just mentioned it, I would say that two things that very much impacted our lives were probably the use of quantum physics in technology and the rise of information theory, right? And you can think of these two things as being real foundations of the way we live our lives today. And in a sense, these steps that happened in the 80s and 90s were to bring these two concepts together, quantum physics and information theory, and ask the question, what can you do differently in information theory if you use quantum physics and have to use quantum physical systems, and also what should be the information theory for quantum mechanical systems. And so somehow I think Feynman, David Deutsch with some steps towards algorithms, and then indeed, like Peter Shor, this discovery of a clear algorithmic advantage for an algorithm that's really something that people see as having a practical application. These exploded people's minds in the sort of fact that the merging of these two could do something. And then I would also go with Ignacio's statement that was an insight into physics, like something else is possible using quantum physics in information theory that you wouldn't have thought before. And then the back action on physics, in a sense, was indeed that suddenly you need to protect errors, and then you get a completely new insight into physics that you can sustain quantum states for as long as you like, as long as you throw enough resources at it. Yeah? And that's a very fundamental change in our perception. I think at the same time, though, in parallel, people, for the first time in the 90s, were able to isolate in the 80s or so, were able to isolate single quantum systems in the lab. And so this sort of comes as a parallel thing that people started asking questions and doing experiments where they saw individual quantum jumps and they were able to prepare specific quantum states. And then the fact that quantum information came at the same time and started to say, well, if you can do that, you can also build computers. This really sprung then a big practical application that people could actually build these things, despite that some people were skeptical, so Cirac and so who were doing these experiments were skeptical about the future, but in the end, people are now up to sort of systems of 50, 100 atoms or whatever system you take, superconducting circuits. It's happening, right? We're building these systems. It's exciting.
Yeah, let me put a little bit of emphasis on that, because I mean, you were discussing about which were the landmarks and all of that. I mean, you were mentioning Shor, Deutsch.
Well, one landmark was Ignacio and
but I mean, theorists, right? But now, let's say you came also to the experimental part, right? And do you believe that this, let's say, at the end, the trapped ions or neutral atoms, the possibility of isolating quantum systems, as you are saying, that was really also a very important point in the development of quantum technologies in general, quantum computing in particular. So that was the point that showed that you could really build the systems. So let's say among all these experimental systems that are being built right now, so this that was the very first one that showed the way. Do you believe so?
There are famous quotes by Schrödinger in the 40s where he was saying that it was completely stupid to think that you can ever have a quantum system alone and experience on that. But technology evolved so much that in the first with photons and then with atoms, so actually the first Charla was 78, first time that they isolated an ion and observed it. And then it came along that now I think we are electrons in quantum dots and so on. And then there was already a magical effect that they could just take a single system and test quantum mechanics with a single system. And that's something that was, even as I mentioned, we were thinking that was completely disparate. And, but then now automatically you think, oh, you can have one, that what happens when you have 2 and 3 and 4 and 5 and 6, and so that you start going up. So first you went down from many to 1, and then you start to grow, you isolate, you get the situation, and you start going up again. And then the experimentalists were fantastic in being able now to start with 2 ions, and 3 ions, and 5 atoms, and so on. And now they have reached a limit in which the complexity that they have in their systems is already so big that you cannot describe with a function. You need so many coefficients as the let's say number of ions of the universe. And so that's happening. That has been fantastic experimental progress.
But I mean, for me, I started in this field late compared to its birth, right? So 2002 or so. But what was attractive then, and I think it's still attractive now, is that the social aspect also of this development has been that across all these different fields, superconductors, quantum dots, ions, atoms, we're all talking the same language and trying to do the same thing. So you can take inspiration from other people's physical systems. And it's very interesting to see, as I said, like somehow experimental constraints are what guide a little bit what you can do. We all have different constraints at some level, and so it's quite inspirational that the field can jump forward in one area, and you suddenly realize, well, I missed something about my physical system. I can draw on that and make an advance here. So I think it's an area where we don't know which of these approaches wins as such, right? We really, but the growth has been fairly parallel in certain senses, and I think it's very interesting to see how it builds up each other, like we all built on.
Okay. So I will make, let's say, now also a jump, not only talking about the, let's say, theory and experiment that we mentioned briefly before, also the hype that is due to the possibility of developing technology, right? So there's also a lot of discussion about how this may influence, and you also mentioned, Ignacio, and you know, Jonathan, let's say how, which is the economic impact of quantum technologies at the number of startup companies and industries that are starting to play a role in all this field. So you gave the numbers before, Ignacio. So I mean, the connections between, let's say, how to promote transfer of technology, or whatever you want to call this term, has been always complicated. So the first thing I would like to ask you about that is, do you think that is different this time? I mean, there are new ways in which you can make the jump from basic research to technology. I'm asking that because, I mean, you measure quite often, which is the time that is spent between the discovery of something and how this goes into the market. So you may think that these times they are shrinking, so that, let's say, the jump is shorter and shorter every time. Do you think that this is the case in this field? Do you think that this is also the case in all this part that is related to computer science and algorithms and things like that? Or do you believe that this is, again, let's say, the same difficulties that were found in the past will be found now again?
Shall I start? Yes. I think, I mean, quantum science is quite diverse. So one should point out that quantum computing is one aspect. There is quantum communication, there's quantum metrology type applications. And some of these are already in market and being bought as devices. That somehow in quantum communications, it's a two-particle system at a fundamental level, and so one can think already of selling systems that work, right? Similar with metrology devices, there are already scanning sensors on the market which are produced from this quantum information sort of world, if you like, which are operational and you can sell. Quantum information, I think, the computing still, to me, seems like something you could say is 10 years off. Of course, this 10 years is a vague 10 years. I don't know when these things are coming. I think it's, from my perspective as an academic, it's somewhat surprising then to see how much commercial interest there has been at this early stage. And we now have a startup coming from my research group, and I think to watch how investors are thinking about this, I think part of it is that they extrapolate a little bit into the future and see that potentially there's a big market there. But nobody knows quite what that market is yet, because nobody knows quite what quantum computers do. Nobody knows quite how successful it'll be to make them. So there's some aspect of a gamble there, but in a certain sense, this early stage investment it's not gambling, because they invest in many parallel channels at once. It is gambling at some level, right? But they parallelize this a lot, so they're able to take a level of risk I wouldn't have expected on any one of those. But in a sense, it is a bit of a gamble on what's coming. Nevertheless, if one projects, or if one looks at what classical computing did, and also people there were skeptical. I read a wonderful article recently where Shannon in the 50s is reflecting on what he thinks about information theory, and my colleague had actually written that you should place quantum in front of information everywhere in this document, and you'll find the state of the play today. Because he was saying it's all very nice and curious, but we know no applications, or very few applications, and it's very niche. And in a certain sense, many of us would say the same thing about quantum information today. Yeah. So I think there is a bit of a risk cycle on it. There is a lot of then noise and hype. The business cycle is very different from academia. They talk about where they will be in a way I wouldn't allow myself to do as an academic, but that's the world in a sense that we live in. Yeah.
I think that in the case of quantum technologies, it's a little bit different development than in some other technologies of the past. And so first of all, the industry entered the field in 2012, around 2012, and big companies, especially IBM or Google, and then they invested, and some of them because they saw a business, IBM, some other ones because this is something that they want to do in order to have the Google name everywhere. So there were different motivations, but actually they can have engineers, they can have something that we cannot have in academia, and this is why in their field, I mean, they really accelerate the progress. So this is something that happened, and this thanks to the industry in part of the thing. Now in the case of atomic systems and ions and so on, it's a little bit different. So if you look at still some companies in the US, Honeywell, that they have ion traps, but I mean, this has been basically developed at the universities or centers or startups. And I think that that's a very good model actually to have it. That's the one that we follow in the mini quantum valley. So we don't, the scientists, let's say, will not build the startups, will build now the equipment and we'll sell them. I mean, but we say, no, we do our science, and then the startups should come here from the young people, and then they will build it, and they will have to build it. We will help them, but they will have to build it, and then they will go on that direction. And in our case, I think that it works very, very well. However, since it's a very long-term investment, then we need the public fund. And then in Germany, this is what is happening. So, I mean, investors, they don't invest for a 10-year benefit. And so that's why we need the public, if we want to develop at the levels where this is happening in some other places. In China, I mean, they have a lot of money coming from the public sector, and yes, because of that. But I wanted to mention something that I found very curious, and I didn't know about that. So I mean, I'm a scientist working in an institute, research institute, and then all of a sudden, from one day to the next one, then you start being visited by investors and people who have a completely different way of thinking. And then at some point, you realize that many of these investors, I mean, they don't care about if a quantum computer will be built and they will sell the quantum computer. What they care is about the value of the company in 3 years. And for them, a hype is fantastic, okay, because it grows the value of everything. And so I'm very happy that investors are pushing and investing, but however, I mean, as a scientist, I wouldn't like to be in the hands of investors alone, because they can make promises in order to have some benefits that, probably in the lab is much more difficult to do. It's a sociological question that never happened, but it's curious to see that now people can be moved by a different interest, and this is happening, and that's actually it's moving our field and creating basically some has certain responsibility in the creation of this big hype.
Yeah. You have this same experience, Jonathan?
Yeah, I mean, it's been an interesting thing. I think I was somewhat, my instinct is to recoil a bit from hype, right? I think maybe that's an academic interest that, like, we all share, right? And I've seen it happen, but I see the other side to it. There are opportunities for the young people coming out of my And that's advancing the science on the level of the university too. So this is a great opportunity to take those weird directions technologically you would never been able to do before. I think that's the sort of thing that the scientific advance, if you can go down these side channels and go for new technologies and things like that, you have new opportunities. We'll discover things that maybe that we wouldn't predict that we would discover. I think this is great for the sciences endeavor. So it's useful.
So maybe if I can add something. So there was a very famous headline in the New York Times when Google appeared for the first time. They did that and many other newspapers. And in fact, this triggered a lot of investment. So people, when they saw that, they started shaking, and the governments also in Europe said, why did it happen in Google and not in our academics? So this shake a lot the system and created a lot of impact. And so I could imagine the situation where in the New York Times there is maybe a headline that says, Google stops its activities in quantum computing. So what will happen? So probably have a very big impact, fortunately, and I mean, this will not harm so much research as one could think. And the reason, I think, is that we have the public sector very much supporting us independent of what is the industrial value. And the reason for that, I think, is not because they believe, well, I mean, they believe that quantum computing will be important in 20 years, we have to invest now. But I think that the driving force there is that they want to have it before China. Okay, so they think that, they know that China is having, and actually this would be a kind of funny situation if all of a sudden a country, China could be any other one, has a quantum computer and they don't share it with the other ones. I mean, they can crack your communication, they can probably start building some drugs and having patents and material, so it could give a big advantage. And I think that the public sector is very aware of that maybe they must not make money, but they want to be in the first front. They have to be prepared for that. And this is why I think that we're safe with respect to this possibility that maybe some investors see that nothing is coming out or it's taking too long, the benefits are not coming, but they still be protected by that.
Yeah, I think countries, I mean, we've had discussions with presidents of countries in the last few years. As an academic, I found it totally bizarre, but it happened in the last few years. And part of it is that countries see what happened with the last technology ages, silicon and so on. And some countries are really built on those industries. Korea, for instance, sees itself as built on the success of silicon, right? It really, that's their mentality. But they also see that silicon is coming to an end in certain regards in terms of how much it can advance, just because a lot of it's been about miniaturization and this can't go forever. Yeah? And then there's a question, what's coming next? Where's the next technology coming from? And of course, many technologies ultimately did come out of physics, right? And one area of physics certainly is quantum physics. And so, in a sense, the threat is that you miss out on this new thing that nobody can quite define or predict. And you're out of the next technology revolution, and then your economy is not the winner, in a sense. And I think that, and especially the China threat, is part of that, right? Or the threat, it depends how you want to see it. But the fact that another country might get there first and have something that you can't quite know what it is, doing something powerful, this is motivating, right? So, I mean, it should be said that I think probably from the experimental angle, one of the main funders of quantum information research over 30 years or so was the US government, right? And it was their military and intelligence agencies. And the sentiment that I get from, talking to them is that, a lot of it is, when is this device going to appear? What's the state of the art? They would like to be informed of where the state of the art is, because it's a threat for them, ultimately. Yeah? And maybe it's not that they need to build the whole thing first, but they need to know if somebody is able to do it.
In a way, we are paying the price of, let's say, the relevance of physics and technology in the past, right? I mean, what I mean by that is that now there are geopolitical consequences to any big technology that is going on. Then, so we have, let's say, all these connections that are not purely physics or science, and many other things, right? And in this respect, I mean, do you have any feeling, if any, about how things are going in Europe, US, and China? So, do you know what's going on in China? Which are the most advanced countries in this respect. Because in China, not always we know everything that is going on.
Well, first we don't know what is going on, so we can make some estimations of what's going on because they don't publicize the funding. And what is very spectacular in China is not where they are now. So maybe you go technology one by one, they're like coming in the top. I mean, what is very impressive is the rate at which they got there. So in 3 years they start the lab and they're leading or top in 3-4 years. So if you just extrapolate what will happen in the future, you see that they have a very, very fast track. And now, but in China, for example, Alibaba, that was had a lab on quantum technologies, closed the lab. Okay. So they closed it, and now it's no longer pursuing quantum technologies. But the Chinese government sees it as a priority, especially in defense or in communication and so on. And they are advancing very fast. But as I mentioned, it's not part of it. Now, US and Europe, well, it depends on the technology, but so superconducting devices probably use a bit more advanced. I think that in ions is Europe, and the guys have been competing very much with the US. In cold atom at the moment is a little bit the US, but I think that this may change soon. So, I mean, there are let me say that maybe something that requires industrial in the US is better, but otherwise in Europe is doing quite well.
Yeah, I think okay, so one of the comments I was with a professor from Tsinghua University last week, and he said there's some giant building being built for quantum computing in China, but he doesn't know anything about what they're going to do there yet. So there's a lot of investment there. I think the other thing you see of the new groups that started there, they brought big names back from, say, the US or so, and these people are running huge efforts, very parallel huge efforts, and they produce some impressive results. They certainly get, as Ignacio says, towards the state of the art, and it's impressive how quickly they build these setups. In sort of the comparison between Europe and the US, I think the US has, I mean, if you look at investor cash or cash to invest in commercial enterprises, the US is much faster to do this, right? So a lot of the private investment in this area appeared first in the US, and Europe took a while to get the idea that startups in quantum computing were a thing to do, and now it starts to appear, but we have a more cautious investment environment. And you do see the difference of that. The big companies that floated, for instance, they were US-based, partly because the professor, I know Chris Monroe, who's the NQ professor quite well, but he had an investor coming to him and saying, here's your paper, this looks like a business plan. And he then got nagged over 5 years, and eventually he caved in and decided to start a company in a sense. And so I think that's a different mentality in a sense that we don't share here.
But also the industrial situation is not the same in Europe that in the US. Let's go to the first the top 10 technological companies that are all in the US, maybe China, but not in Europe. And so this makes that they have the possibility of investing and moving much faster. Also, the regulation in Europe is much more difficult to have such an industries as compared to the US. So there are many reasons for that, but the industry part, it's very clear that the US is leading and have a very better position.
Do you think that part of the hype, and in particular of these investors' hype, is also due to the big companies like Google, Amazon, IBM that, they started investing in quantum computing, let's say, from a very early point, I would say, right? So when you see that these big companies, they are investing in that, there might be many people that say, come on, so this might be profitable in the future. So do you think that we can somehow blame, I wouldn't like to use this word, let's say, that was part of the reason for this, this hype was growing?
I think, as soon as they're involved, these companies, then their name picks up hype regardless of anything else that they do. And sometimes they're using that, right? Sometimes I think these announcements in quantum make them feel like a cutting edge or look like a cutting edge company, and this is advantageous for recruitment and all of these aspects for them. But it's certainly true that I was at a tennis lesson of my kids chatting to the guy next to me who was an investor. He told me he was a sustainability type area investor. And the minute I mentioned that, I said I'm interested in a startup company, whatever, we were chatting. And the minute I mentioned that Google had a significant effort, he wasn't a sustainability investor anymore, but he was wanting to invest in a company from mine, right? And I found that kind of crazy, but you can see that they have commandeered such huge resources that anyone who's in an investment environment is looking towards what they're doing and hoping to be bought by them and things like that, right? So it has a huge impact on anybody who's involved in money, whether these big companies are involved regardless of anything else.
Well, I think that they are used by some other people to create the hype, but themselves they don't create the hype. So I mean, Google, for example, is fantastic. I mean, how they think. I mean, they basically the approach that they took is to buy a university researchers and to put them, give them money, and to create that. AWS has done something very, very similar, and they have just taken team up with the people from IMQ, with the people from Harvard, Clivia, people from Caltech, and so on. And so they really take the expertise of the universities, of the academic, and then try to build out of that just by putting industry behind. In the case of IBM, they didn't have to team up with the university because they had themselves some researchers that are very good and that are doing basic research, so they have them then there. So these three companies, at least these three companies, and we could talk also about Intel and some other ones, I mean, they have really taken seriously and done in a very serious way. Now, if other people want to make a hype just because of that in the way that you mentioned, because this can happen, and this will happen with not only quantum computing,
Yeah, sure. I mean, I didn't mean that they were doing that on purpose, right? I mean, that somehow when you see these very big companies that they're investing in a field like that, it's like saying, come on, so this is something serious, right? So then.
Yeah, but the difference is maybe that some of them they are not expecting benefits in the short run, and some of them are expecting benefits. So that also makes some difference.
Yeah. Okay. So let me also now go to something that you, I think, briefly mentioned, Jonathan. Perhaps you also did, Ignacio, which is, I mean, we have been discussing a little bit about quantum computing and so on, but you have many fields. You mentioned that also in your talk, right? That can be related to, let's say, they can be included in this general topic of quantum technology. So you need to talk about computing, communication, or even simulation as a different thing, or sensing, metrology. So you have different fields. So do you have any idea about which one of them you consider that can be more advanced at this point, or that can provide, let's say, more spectacular results in the very near future? Because we are often talking about, let's say, in the next few years, but these few years could be shorter or longer depending on the field. So how do you feel about that?
I mean, spectacular results is a broad thing. I think all of these fields, they're at a frontier at some level, right? And there are beautiful results coming out in many areas. I think your eye is taken by a few, and probably it's very visible which results come up. I think in the measurement sense, then it's been impressive to see how sort of atomic-like systems can be embedded in solids and placed in, I would say, weird scenarios where you wouldn't think to put measurement devices before, but suddenly you can interrogate at the microscopic level structure of matter. People have been doing that with now superconductors, I think, under very high pressure and things like this. And so some of those are impressive. I wouldn't, a few years ago, have seen that application come. For me, that's what's spectacular about that sort of thing. I think other than that, I mean, one always has a perspective from one in the field. I think there are many spectacular advances going on, for instance, in quantum computing at the moment. They're just not a quantum computer that works yet, right? So in that sense, then, the science there's a lot of excellent science going on. I think it's very diverse and it's very interesting to see how it's evolving. But where are the next applications? They're probably in the smaller elements, either building blocks or measurement devices, or as I say, cryptography is just an easier problem to
Well, so I think that there is one application, let's say, that will affect us directly in the short run, and that's post-quantum cryptography. So, as you know, quantum computers can break codes, and now we expect that quantum computers could be able to break codes in 10 years, maybe 15, 20. But this means that in 10 years, then they will be able not only to read the secret messages from then on, but also the ones in the past. And so some people don't want the messages to be read in the past. And so that's why they start now saying, so what can we do in order to protect ourselves from quantum computers in the future? And then there are two ways. One of them is to use QKD, so quantum communication. And that's still on the research areas. You can do it over 50 kilometers and so on, but it's not very scalable, it's very slow, it's very expensive, you have to change the hardware. But there is a simpler way, which is to change the software, which is this post-quantum. And so now then the American government has already has said that they have to change already. And so I think that Google and some other companies, they already did it in the past, but that's something that is happening. And so more and more we will see how they will change our cryptographic systems just to protect. And also these are some other, let's say, protocols that they have to know a little bit of quantum physics because they have to be protected against quantum computers. So I think that this is something that is going to affect us in the short run. And actually there's a good business on that. I mean, you have want to create a company that is going to implement some post-quantum cryptography and systems in other companies and so on. So maybe there is a possibility of making some business. Now the other part, which personally believe, so this is you say it's very personal, that would make the big breakthroughs, I think, will be related to quantum simulation. So we have it already happened. So the group at Harvard, so 2 years ago, they did some experiment with the quantum simulation and discovered something that nobody knew. I mean, some, let's say, property of quantum many-body systems that people didn't know. And then this triggered research, and then, so this is what's called quantum scars in many-body systems, triggered research, people understood it, and so there might be some other discoveries like this one, because there are now many people who have these quantum simulations. And so it will not be maybe that they were able to solve some specific problem, maybe to look at QCD with, let's say, chemical potential or something like that, some phase diagram, but maybe rather just to try to start discovering, and I think that that's something that will happen more and more.
I think, yeah, both of those have an interesting aspect, which is I think that fundamentally if you asked at the end of the story, what did people know, it would be a new thing that they could do classically. The post-quantum cryptography is all classical, right? And also in the case of algorithms and people playing with these systems, a new phenomenon comes available, which in the end somebody can describe very well, but they would have never tried to describe that. And I think another impact that's happening is that people are now bringing problems to people and saying, could this be done on a computer? But that gives a bunch of people who are used to thinking in weird ways about algorithms access to interesting problems that people have that they didn't know about previously. And then you see advances in the algorithms for doing those problems without any quantum computer yet existing, right? And in fact, I think when I think of the tensor network stuff, this also is inspired a bit about thinking about quantum computers and then realizing that actually there are very nice compact descriptions of things that came out of that. So there's been a lot of back action on the classical computing and classical information field, I think already, without these devices really being successful devices in their own right.
Okay. So I will open also some time for questions. If there's any from the audience, I may need some help because I confess I don't see anything with the lights. So if there's any question in the audience, please raise your hand and I hope that someone can help us to. There's one there. I see one there.
Well, thank you very much for this interesting discussion. From my perspective, these days people have gone either full analog quantum simulation or full error-corrected quantum computing. But do you think there's still room for some useful research in the frame of noise intermediate scale quantum devices, like, for instance, variational quantum algorithms and so on?
Definitely. So I think, you see, if you look, I mentioned that a bit in my talk, so you look at 18 years ago, they developed a classical computer, the applications were basically the same applications that we know now for quantum computers. However, once they have the equipment with them and they were building and improving, then they discovered many other applications. And I think that something similar will happen with these devices, and so that you have to put it in the hands of the people. I'm not so optimistic with respect to some of them, like these variational quantum algorithms, at least with the current levels of noise. And the reason is because, okay, so when you do serious research about applications of these quantum systems or some problem, Then, when you compare the performance, you should not compare now to a classical algorithm that has a perfect performance, because your system has errors. So you should compare with a classical system, and you allow also to give not the best result, but a good result. And if you make this comparison, then it's very hard to beat the classical methods, because the classical methods have been working for now 60 years. They're working very well. They have been used by companies, by industry, by many people. So it's a very big challenge to beat them. So, but however, I always give an example of certified random number generation. So you see, 4 years ago, nobody could have imagined that a quantum computer can be used not just to solve some optimization problem, but to generate certified random numbers. And so certified random numbers is a number that is random, and then you can make sure that it's random. So classically, there is not something similar. So when you play lotto, and then you see the balls coming out, they could have been tricked. Okay, so people could have just selected a number and make such that everything at the end was the number that came out. Quantum mechanically, this is impossible with a quantum computer. And this is an example of something that people could not think in advance that something like that would exist, but when they started thinking about application, they came out with this idea: you can do things that are not related not with solving a problem, but are related to something else. And I believe that these devices will help in these kind of things that are difficult to predict.
Yeah, I think when I look at the structure of most quantum algorithms that I know, that the remarkable feature of them somehow is that they use interference in a very intricate way, and they usually produce almost no entropy in the sense that they produce the answer, but they don't produce any other information. What this means for a quantum computer is that, in a certain sense, errors can be very bad. So what you need is an output that's going to be very robust to the type of errors that you have. I think there's, for me, quite a bit of hope that that can happen in physics problems, because these physics problems, the answers we have in physics must be robust to the world around them at some level. It's less clear for general purpose problems that that's going to be true, because usually you're looking for an algorithm that solves something very specific. So I think these NIST devices, they're very nice in giving you insight into what quantum computers may be able to do. I think they've given surprises. Some of the answers that they give are stronger answers than one might expect, given the mess that occurs. I mean, it is a mess after a few steps. But they probably, my feeling is that the error correction will be required for most of the practical problems you think of, and certainly for guaranteeing precision of answers. Outside the sort of direct physics and energy domain, I think they probably have limited scope, but they're great playgrounds to stimulate us to think of new problems, and I think that's a big value. They look like toys. They are toys at some level, but that's stimulating, and when you look at the use of computers today, partly we got there because we use them as toys. Yeah.
Any other question?
Here. I don't know whether one or maybe two. So the first one more related to physics and, for example, solid states. When you have interactions in the lattice and so on, you usually interact with neighbors. No, you have the exchange integral, which decays exponentially. So you interact with relatively little neighbors on the one hand. On the other hand, as you told, the configuration space when you have many single particle systems explodes also exponentially. So in a sense, does it somehow compensate? And maybe the system is not as complicated if you look into it in practical cases?
So I'm not sure if I understood the question correctly, but even if you have short-range interactions, if your decay is very short-range, then you can have very difficult problems that you cannot solve with classical computers, but you can solve with quantum computers. You can show that you can embed, let's say, BQP hard problems into the ground state of local Hamiltonian, just with interactions next near neighbors. So that doesn't certainly, I mean, the fact that they're short-range doesn't mean that it's easy with a classical computer. Now the other part, I'm not sure if it was related to that. Now what happens now if there are uncontrolled interactions? You have a system, and then you try to do your qubits, and then you start your interactions will not be controlled. Maybe as there are some external fields, and so on. And in fact, this kills, I mean, this has an exponential bad law that compensates the good law. You can understand it very easily. You have n qubits, or 10 qubits. Then the probability that nothing happens to all of them is the probability that nothing happens to the first, and the probability that nothing happens to the second, and you know that the probabilities of n's is the product of probabilities, so it would be p to the power n. So it decreases the probability that nothing happens, decreases exponentially, and this compensates the gain of quantum computation. And that's what people thought when Arosh wrote that paper, that quantum computer would be impossible because the exponential gain has exponential error. But then Peter Shor came along and showed that you can correct and get rid of this exponential, say, bad decay just by repeatedly correcting and correcting and correcting. And so for the moment, we know that at least in principle, and now starting being practices, Jonathan mentioned, then it's possible to, to let the quantum advantage win with respect to any, let's say, if the error is sufficiently small, but independent of the size of your system.
And then the more maybe social question is, I mean, and you pointed towards that, I think, if this is really such a powerful technology and will influence maybe even the way we think and artificial intelligence, I mean, how large is the danger that this is just in the hand of few, one company or even one state? And do you, I mean, I had the feeling that this is a concern to you.
Well, it's the same concern as that a supercomputer would be built, a classical one, and would be in the hands of somebody that would use it to do something bad. So it's not a quantum technology, it's about any technology. It can be good hands or bad hands, and so the political people should be responsible of regulating in such a way that it's done for the benefit of the humanity. But that's not different from some other ones. My concern, and it's not my concern, I think that is the concern of the politicians, is that then once another country has, then it has a power with respect to developing drugs, developing materials, developing something, strategies, maybe using for optimizing, I don't know, whatever, and then they have a very weak advantage, industrial advantage, military advantage, and whatever advantage. And as you know, I mean, the countries don't want the other ones to have advantages, and that's why the concern is behind that, and why I think that the politicians and the governments support very much the development of quantum computers in Europe, in the US, just to compensate this risk.
So I would agree with that. I think this is a common risk of many technologies. Computational technology is somewhat hard to define where it's going to go, and I think quantum computer, that's very true. We don't quite know what they will do. We know a few specific cases of things that they may do, and indeed, people can use computational devices in good ways, and even making drugs can be a good thing or it can be a bad thing, right? Depending on exactly how you tweak it. So I think that is a risk that needs to be considered. I think what you have to do, you have to understand where that technology is and where it's going. That's the information input, and then as governments you have to react to that, and fortunately for me at some level I can advise, but other people have ways of making decisions and trying to think how best to react to those sort of decisions.
Yeah, but in a sense, with classical and many other fields of research, a lot of basic research, most basic research was published, was kind of open, and then it was more a point of view of running just for the technology to make maybe better computers, thinner path in silicon industry. But now my feeling is it's even fundamental that maybe this knowledge, basic knowledge in science, is not shared.
No, I don't agree with that. I think that it's completely shared. So as we public our thing, so the only thing is that, of course, if you start looking at how to do that in a different way that is better, and you patent it, and then you will not publish until 1 year or something like that. There are some rules for that, but everything is publicly, even by our, let's say, Chinese colleagues or whoever. Everything is public. I don't see that benefit.
Yeah, I think to some extent, I would agree that still things, it's surprising to me how much startup companies even publish about what they're doing. Probably the details of some fabrication process one doesn't find out, but in a sense, certain levels of dark art to how these things work anyway, right? So some of that is hidden. I think also historically it's not true that everything has been published. There's certainly been research done in companies and also in governments that was never published, and we found out 50 years later that in parallel with academic research, governments were working on this and had pretty good solutions. But so this is part of our culture in a certain sense. It will happen. At the moment, my feeling is most people are publishing quite a lot of things because they get recognition for that still from that they're a leader, and that's still important for recruiting good people and all of these things. So I think it's in the open.
But I agree with what you say, that it's not different from some other. You have fundamental research, this is public, and at some point you start building devices, you have to patent, but it's happening in all technologies, and it's very normal.
Yeah, so I think this is a long discussion, let's say, along the way about, let's say, the basic research that is done with public funds and also the protected research that is done with companies, right? Within companies. But in this respect, I mean, it was mentioned before that, you know, that in the Basque Country, so there's a large initiative in collaboration with IBM. Let's say the Basque government invested a lot, not only to bring, let's say, a quantum computer to the Basque Country, but also to develop joint research projects with them, and also some training. You also mentioned that Google, for instance, they also have this kind of collaboration. So I think that this is also, let's say, a good way to go in which you can have, let's say, some combination of, let's say, basic research, applied research, and this is a model that could be, let's say, profitable in the future.
I think it can be. I think one has to be, I mean, of course there are relationships between big external players and also local players. I think one has to make sure that by investing in the big players, one doesn't limit the investment in the local players. For instance, is there a startup in the local area that wants to produce quantum computers, and now they see the money is going out to an American company? I think there has to be a good balance here, and I think people have to be focused on the fact that I think the end game for a region should be to invest in their region, and there's a balance there between how much knowledge you bring in and how much knowledge you build up locally, and I think one wants to invest in your local people. That's the need.
So I would add that I think that it's very important, the education on quantum science and technology. It's not something, statement coming from academics. This is coming from the companies in Munich, for example. They're not so much interest now in using these quantum computers, but they want to train the people such that when these next generations of quantum technologies come, they will have the people there, they will have the market to go to, they will have the talent around. And that's, they have experienced what happened with artificial intelligence, and so they are paying for that, but they didn't invest in the people just thinking that this would be a technology that will not work for many years, and they don't want to make the same mistake with quantum technology. This is why they're pushing very much for the education. And in this sense, I think that what you're doing with IBM will bring you in a very special position to have an education, like a hands-on education on how to use quantum computers. Now, I think that this will be also important maybe, but we also have plans for that, to complement on how to build quantum computers, how to develop this technology, not only just to use it, which is for the software, but also for the hardware. But I think that they both can complement very well.
Okay, so I think we are a little bit delayed in the general program, so I think we may close the dialogue here. But before closing, I would like to allow you just some 1 minute, 2 minutes if you want to say something. And may I also ask you a question? Do you still enjoy doing physics? Are you still excited about doing physics? Do you like it? So, just to finish, do you?
I love doing physics.
Okay.
I think that's why I come to work in the morning. I think, I went through a phase where actually I found the hype on social media kind of it harmed me, and then I took a decision. I have to ignore it and just enjoy my physics, and since then I had a great time again.
I also love doing physics, and I still do my calculations, write my codes. But I wanted to finish maybe with something, some statement that's, so we are living a very extraordinary moment. So typically when there's something happening, then you don't realize 30 years after that, oh, look at the guys, how lucky they were when they developed quantum physics and Heisenberg and all these people around. And I think that this is to some extent happening now with these quantum technologies. And so I would say that it's a very good moment now to step in and to enter the field as a young person, because I mean, this is going to develop one way or another. Maybe it's not quantum computing, sensing, it's some other thing, but it's a very good moment because now we have transpassed the frontiers of quantum physics. We're able to control this world, we're able to understand it, and so that's something that is coming one way or another. And it's fascinating, and it's a really fascinating field. So I think that for the young generations, they are maybe not represented here so much, but for the young generations, a very good subject to follow.
I would agree with that. I think one thing that's kind of special at this moment compared to my upbringing as a physicist is that now you come in and you're a physicist, but you're in classes with engineers and computer scientists. They're all attending my computing class. And this is just great for your mental stimulation, right? To have so many different types of mentality all working on. It's a lot of fun, and at the end of it, there seem to be lots of opportunities for diverse jobs. So I think it's really a great place for people to be in.
So yeah, I was going to close to make some kind of statement, but I think after these two I will not be able to improve that. So thank you very much to both of you for being here.